is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, thanks Anna for the introduction, and good day to everyone. Thank you very much for joining the session. Welcome to the AI for Good Machine and 5G Challenge webinar session. My name is Thomas Bakos from ITU, the International Telecommunications Union. The Machine and 5G Challenge aims to create a community to solve network-related problems using machine learning and artificial intelligence. Today, I'm very excited to host a webinar titled Next Generation Wi-Fi Throughput Prediction. This is quite an interesting session because the session or the challenge was run on Zindi platform, and we are here to report on the solutions, on the results that we have received in this challenge. Is quite interesting, so I would like you to listen carefully and be participating in this webinar. And without further ado, I would like to introduce the speakers of today's session. We have David Nunes from University of Pompeu Fabra in Spain. We have Gaurav Saha from Mahindra University, Arabi Bojesomo from Khalifa University of Science and Technology, and Hamdi Bakos from École Polytechnique de Tunis. They will discuss the use of machine learning to predict the throughput, which is the performance that a subset of access points can achieve in CSR network. This webinar will introduce the winning solutions on the next gen Wi-Fi throughput prediction challenge offered through Zindi. So it's time to welcome the first speaker, and I would like to welcome David. Good morning, David.
Morning, everyone.
So the floor is yours. You can start off the presentation.
Okay. Can you hear me properly, Thomas?
Yes.
Okay, perfect. So let me share my screen, please. Okay, can you see the window of the presentation?
Yes.
So that's perfect. Well, this is the presentation that we used to present the challenge. The idea, as you said, is to basically to predict the throughput in coordinated Wi-Fi networks using machine learning, basically. So just to recall a couple of things about we did kind of a similar challenge for 2021, and then by then we explored several techniques of optimization using federated spatial reuse in next basically generation decentralized .11 wireless LAN, but by exploring the feasibility of applying machine learning in next generation wireless LAN, specifically through the use of federated learning. And in our case, this edition pretended to extend the work of this edition of 2021 edition, but now in the context of coordinated Wi-Fi networks. So for that purpose, well, just to recall a couple of things about coordinated spatial reuse, the idea is to exchange access points, exchange information to coordinate the simultaneous transmissions. And the simultaneous transmissions are succeeded only if APs are suitable to transmit at the same time, which means that if the signal to interference plus noise ratio, SINR, at the receivers is high enough to allow to the receivers to decode properly the frames. So, well, as you can see, the higher, as you can think, the higher the SINR at the receivers, the higher the modulation coding scheme and CS index, and so the data rates. It will allow to devices transmit using higher data rates. Well, just to sum up, the idea of using CSR is to find the best, or the idea is using CSR and finding the best combinations. The idea is maximize, in our case, the aggregate throughput. Okay. Well, this is the setup that the participants used in the data set. Basically, we simulate several different scenarios, which with this scheme, 9 APs in grid. Each of them was centered in a sub-area of 10 by 10 meters. The number of stations associated to each APs was randomly selected per deployment. It was a random number between 1 and 5. And these stations were also uniformly deployed at random in each sub-area, okay? The downlink traffic was evaluated, downlink traffic in saturation conditions, and the path loss used was the path loss model for IEEE 11AX. Well, as inputs, we gave the participants the first parameter, or the first data we gave them was the RSSI matrix, which is something like this, a matrix that contains the received signal strength indicator, or RSSI, in the dBms seen from each station when every AP transmits, with this format. Kind of, for instance, in this grid, we have the RSSI associated to, I mean, the RSSI that station 1 receives when AP1 transmits, and so on for the rest of the grids. Then, well, the scheduled IP-STA pairs contains the list of pairs for a given transmit opportunity. Okay, these IPs will be selected to transmit simultaneously to their corresponding STA using parallel transmissions or CSR scheme. The maximum number of APs was constrained to 4 APs, which means that only a number between 1 and 4 APs could transmit in CSR mode at every TX hop. Okay, and that's an example. For instance, here it means that AP1, because it's the column 1, AP2 is the column 2, and AP9 transmit, all of them transmit to one of their stations. For instance, AP1 transmit to station 3, AP2 transmit to station 4, and AP9 to station 25. And that's the idea with this format, this in the dataset basically. And the idea with these inputs, participants in the first problem had to estimate the throughput, okay, based on this data. Different deployments, we generated 10,000 different deployments where the number of stations as well as their positions were randomly generated. The number of stations between 1 and 5, as I commented before, and the position was a number. I mean, is the number of stations was set to 3, means that 3 stations were associated to each IP, and then they were randomly placed in each sub area. For each deployment, then once we created a deployment, we simulated 100 different TX hubs, okay? And in each of them, APs and STA pairs were randomly generated. That's the idea of the dataset. And as an example, in deployment 8, for instance, this is the first rows, n rows, were for the RSSI matrix, and then 100 after that 100 TX hubs, which means 1 row for every TX hub, indicating the transmission pairs. Then the first 9 columns were the transmission pairs, and then the throughput for these transmissions. Okay, so well, this is dataset explained. I don't talk to because you know all of this. And then this is an example. This is a kind of note, interesting. If the SINR value is a condition we put to make this situation more real, if the SINR value falls under a certain threshold, around 5.7 dBs, the throughput is set to 0. It means that the station or the receiver basically wasn't able to decode the frames properly. It's kind of a real effect. Okay, so with this data set and all these conditions, the idea was to predict or to build a machine learning model able to predict the throughput that a subset of access points transmitting at the same time can achieve using a coordinated spatial reuse scheme. Using a set of 5 for training, the participants will be able to train a machine learning model that estimates the throughput for a given set of scenarios, only with the information about the RSSI matrix and the subset of APs, the pairs selected to transmit and or receive at every TX hub. We provide the aforementioned data set for training, and the throughput with the throughput, the training data set contained the throughput values for every TX hub, And the idea was to propose a machine learning model, and this solution evaluated in the test data set couldn't contain the throughput values. That's the idea, having a model, a trained model. They had to estimate the throughput for the test data set. That's an idea of the throughput prediction. This is an example of the data set without the throughput values. And the idea was to be able to predict these values for each TSR at every deployment. So, and the second part is a kind of, well, using the solution presented by for the throughput estimation, participants had to be able to select to estimate the combination around every AP that achieves the best aggregate throughput for every deployment, and constraining the number of AP to at most 4, and explicitly indicate the AP-STA pairs in each case. That's a kind of application using the first problem. And this is an example. For instance, given this pair, P2 transmit to station 7, participants had to build or to find the best combinations that maximize the total or the aggregate throughput. In this case, for instance, we found that the best combination, or one possible best combination, is AP5 transmit to station 15, and this is the result of throughput. Okay, this is the throughput for the first pair, and this is the throughput for the other pair. Okay, and of course, aggregate throughput is the sum of them. Okay. And that's all from my side in terms of the problem or the challenge related to the scenario, the data set, and all questions or problems I mean for the challenge.
Thanks a lot, David, and for introducing the technical part of the problem statement. And now we are going to deep dive into the solutions, and I would like to invite Gaurav. Hi, Gaurav, good afternoon.
Good afternoon. Hello, Thomas. Hi. So, can I start?
Go ahead.
Yeah. All right. Okay. So, good afternoon, good evening, and good morning to people around the world. So the topic, as David pointed out, was about throughput prediction of next generation Wi-Fi, and I am Gaurav. I'm assistant professor in the computer science department of Mahindra University, and I'm going to present my solution. So I will start where David stopped. So here is the situation. There is a room, consider, all right. So there is access points, the triangle, which are the transmitters, you can say, wireless transmitter, and the stations, which are the receivers, all right. So a transmitter, a receiver, and they're going to transmit. The transmission between them is characterized by something called as a received signal strength indicator. So higher the strength, the better the communication between this API and this STAJ, right? So that is the kind of the intuition. And there are two objectives, as David pointed out. For the first objective, the input is the set of AP-STA pair and the RSSI matrix, and the output should be the throughput of a AP-STA pair. I will make it clear more about this. So this was objective number 1. And for this, I developed an ML-based solution. Please give me a yes if people can hear me. Thomas, please. And
Yes, we can hear you properly.
And the objective number 2 is, given an RSSI matrix, receive signal strength indicator matrix, and the number of desired APA-STA pairs, say it can be 2, 3, whatever, we have to find the set of APA-STA pairs that maximizes the net throughput. Okay, these are the two problems. So we will talk about the problem number 1. So objective 1, which is about predictive modeling, the ML part of it. All right. So here the set of APA-STA pair is shown over here. So AP1 is connected to STA1, AP2 to STA2, and AP3 to STA3. So the number of pairs is 3 over here. And we want to compute the net throughput of this AP2. Okay, so it is highlighted in this bold over here. So based on the domain knowledge, we know that, well, of course, the received signal to strength indicator between AP2 and STA2 will definitely help that. So as RSSI 2,2 increases, the throughput will increase. But since this transmitter is all, AP1 is also transmitting and AP3 is also transmitting, there will be some interference, right? So intuitively speaking, as RSSI 1 and RSSI 3,2 increases, the throughput will decrease, right? And this I know from domain knowledge because I am from this wireless domain. And so basically the throughput over here, which I'm telling mu from access point 2 to station 2, will be some function of the signal to strength. I'm sorry, what happened? Just excuse me, please. The signal to strength matrix between these two pairs, and also the signal to strength matrix, the signal to strength values of other access points. So it will depend upon RSSI of this link, RSSI of this link, and RSSI of this link over here. Now, based on, so of course, what we can do is we can simply compute this F using the ML model, right? That's where the computing this F is where the ML model comes into picture. But first of all, we have to make the data set also. The only part about making the data set that I want to highlight is, so we have to make columns, right? Which are the features. So the first column, I suppose I want to predict the of STA2. The first column was of the primary link. Okay, the RSSI of the primary link. This is the primary link. And then there will be RSSI of the secondary links also in the descending order of its values, RSSI values. Okay, I did this descending order because I found that this increases the performance. Okay, so that's what we have. So accordingly, so it was told that there will be either one pair of transmitter, 2, 3, or 4 pair of transmitter for each combination. So I made one model for one transmitter, another model for 2 transmitter, and so on till 4 transmitters. So 4 models were there. For each of the model, I trained a XGBoost regressor using a 4-fold cross validation. And I told you how I made the training data. And why did I choose XGBoost? Is simply because in many ways, as far as my experience goes for ML competition, which tabular data sets, XGBoost is almost like a de facto in many ways. Also, it gave me a very good performance, almost zero, or not almost zero prediction error, which was very surprising. And during the testing or the prediction phase, when we are submitting our output, we basically, as I told you, 4-fold cross validation. So we have 4 models. We took the average. Okay. That is my solution for objective number 1. Now talking about objective number 2. Okay. So again, what was objective number 2? What was given? The RSSI matrix. All right. And the number of the access point and station pairs. Okay. Let that be called M, where M is less than N, where N is the number of APs. So if there are say 9 APs, of course, AP-STA pair cannot be greater than 9. And we want to find the set of AP-STA pair that maximizes the net throughput. Okay, this is the second objective. So the solution technique is something like this. We divide, it's a combinatorial optimization problem, as we can see. I'm sorry, this is getting blocked over here. So it's a combinatorial optimization problem. And we divided it into 2 cascaded optimization. Optimization problem 2 and optimization problem 1. So the overall objective of optimization 2 is to give out the set of optimal APs. So optimization problem 2, find the optimal set of APs. So for a fixed set of APs, it will fix a set of AP and give it to optimization problem 1. So that is given for optimization problem 1. And then the optimization problem 1 will spit out the best pair of AP STA pair for the given set of APs that is given. Okay, so this is the overall architecture and the flow diagram. So I will talk about optimization problem 1, which was basically the APs are given and we want to match each AP with a station. Okay, so we want to match a transmitter with a receiver. So this is our original RSSI matrix. I did not fill it with any value. So this is the matrix, so which has 7 access points and say 12 stations. All right, total 12 stations. All right, across all access points. And then say M is equal to 3 over here. So the number of AP-STA pair. And the optimization problem 2, the given set is 2, 3, and 6. So access point 2, 3, and 6 are given by the optimization problem 2 to optimization problem 1. So we will focus on them only. So 2, 3, and 6. Okay. So this is a modified RSSI matrix. Now, so I will give you an overview about how optimization problem solves. So pseudocode. So for this current RSSI matrix, it will find the cell which is the highest RSSI value. Okay, let it be this cell, which is corresponding to station 3 and access point 6. So basically for access point 6, it will choose station 3 as the station, right? The reason is access point 6 is transmitting. If this is the highest and you are not choosing this for station 3, it will create interference, a very strong interference, which cannot be mitigated by other access points because they do not have that high RSSI values, right? By the definition of this cell over here, because it is the maximum one. So what we do is, as I said, match access point 6 with station 3. And then we remove this row corresponding to station 3 and this column corresponding to access point 6. And we are left with just this, the white columns will be your modified RSSI matrix for the next iteration. And this will have a time complexity of m square n STA being the number of stations. And though I did not prove explicitly, I am quite sure this is the optimal algorithm for optimization problem 1, which can be part of the paper that we want to write. Okay. And now the optimization problem 2, and with that I will end. So optimization problem 2 is basically in many ways a brute force, which is okay for this problem over here. So what is optimization problem 2? Mind you, again, it chooses the set of MAPs. Okay, so let the set of MAPs be this calligraphic A. All right, so it gives this A to optimization problem 1, and it gives out a set of best AP-STA pair, which is this function H for a given access point pair A. Okay, and we know that we can use the predictive model that we just developed for objective 1 to compute the net throughput of this AP-STA pairs. Okay, then what we can do is, then the problem is simple. Iterate over all combination of AP-STA pairs. So that is, suppose there are 9 and M is 3. So 9 taken 3 at a time, combinatorial. Okay, so that many values we have to iterate through, and it is over here 126. Okay, this is approximately 126, which is okay. We can do that. That much of brute force is acceptable. As a future work, we want to, my goal will be to develop more heuristic to solve this combinatorial optimization problem. I think this will be NP hard, so we have to go for a heuristic and possibly performance bounds. All right. Thank you. If there is time for any questions, I can answer.
Thank you so much for the presentation. We will take the questions towards the end of the 3 presentation. We'll have the discussion for everyone. Now okay. I would like to move to the next presentation. So Arabi, good afternoon. Please unmute.
Good afternoon, everyone.
Yes, the floor is yours and you can share your screen.
Good afternoon, everyone. Can you hear me, please? I am Arabi. I participated in the next gen competition in Zindi about prediction of APs, throughput, the TP of APs in some transmission scenario. As an introduction of my solution, I believe machine learning is all about domain knowledge. However, some domain knowledge can be transferred from an idea to what we have at hand. Based on the requirements, we are given some set of APs and some set of stations meant to be precise, and we have a possible number of APs that could connect with each of these stations. And from understanding of domain knowledge of transmission, it is normal and natural that interference is all that is important. When there is interference, there is a tendency to have a kind of a modified throughput for the set of APs that are in operation. And based on this, my whole solution is relying on interference of the AP that are available at any point in time. Now, let's to start with. If we are given a transmission option where we have like 5 or 6 APs in that are actually in operation, obviously, and we have to predict the throughput for each of these APs, then we have to consider the APs that we want to predict the TP for, as well as the interfering APs, to see what effect does the other ones have on this particular considered AP. To this end, for my solution, I focus on getting the interface into play. And to get the interface, I try to put some idea of interface from different scenarios. And one of the first things that I considered here is to use differences. What is the difference between the AP that I want to find the TP for and the other APs that are available? And this is intuitive enough to show that if one AP that I'm trying to get the TP for is far more greater than the one that I have that is trying to interfere with it, there is a tendency that it might have an impact on what is expected of the final TP for this particular AP. The other thing to consider is that looking at the idea of a signal to noise ratio, I picture the other APs in existence as a form of noise. While the AP I'm trying to find a TP for, I see it as the actual signal. And to that end, I try to compute some kind of a simple ratio, which is just the ratio of the RSS for the AP that I'm considering and the APs that are available in this transmission. Of course, I don't convert this one to decibel because I'm using a machine learning model, which I believe that it should understand this idea of ratio rather than converting this one into decibel. While the final kind of a way of extracting my features is to look at some form of the normalized ratio. When we consider ratios, I see that one to be a bit prone to some kind of noise, as well as differences, because when I try to find the difference between an AP and other AP available, it's possible that the AP I'm trying to find the TP for is actually smaller than the AP around it, like the APs that are available. And for this reason, it might be logical for me to consider some form of a normalized ratio of this, where I consider the difference and I divide this one by the sum of an AP and the interfering AP. And doing this, I have a 3 set of possible features to train my network with. However, since we have a lot of APs in the system, based on the varied number of APs or any particular kind of a transmission, there is a need to aggregate these features to have equal number of features for my training and also to ensure some kind of to avoid having unnecessary LAN in my training set, because if I just put all these things into use without considering some kind of aggregate, I might end up having some kind of NAND which may not be that productive or advantageous to my network that I plan to use. And for this reason, I decided to use some kind of aggregation. But I limit my aggregation to be simple and to be of first order. And that there is always a reason for this, because I believe that machine learning, irrespective of the domain knowledge that we have, has to be channeled to the task at hand. I believe after some kind of EDE, like some kind of exploratory data analysis, that most factors that could affect the final TP prediction is of first order. There is no need for me to consider second order variations like standard deviation and the rest of that. And so for this reason, I focus on the mean, the median of anything I found in terms of what is the mean of the difference for this particular AP? What is the median of the difference for this particular AP? And thinking about the mean and median for the simple issue, and some other kind of aggregation that I deem fit after my analysis, which include just finding the minimum and maximum and the mean absolute deviation. The reason for this thing is more that is based on the fact that if I just decide to use mean and median and the likes, I might my model might be lagging some kind of intuitive features, which include the minimum and possible maximum that could be in this range, so that the model can have a kind of link to decide on. Like, since this is the minimum that I could get and this is the maximum that I could get, then having a particular mean value is going to help the model a lot. So this is the final details of what I did in terms of getting the features. And as I mentioned earlier, it's all about interference. And to the machine learning approach that I use for this particular task, I specifically decided on using LGBM light boost, basically a light RGB. And the reason for this is that the feature that I have is mostly numeric, and just a very few number of I can even say one categorical feature, which is the number of AP that is actually interfering. Because besides finding the feature that are related to interference, I also look at what is the number of interfering APs at the time. Because I found out that if I have a less number of APs interfering, it is obvious that the deduction in the throughput prediction will be minimal. So because of this, I decided to use the number of APs interfering as part of the feature, which obviously happens to be a categorical feature. Going by that, for the machine learning approach, I use a LGBM, which is just a simple light LGB, a light GBM kind of approach. And another thing that I would like to mention in this particular challenge is that why it is expected that we should predict something that is and also the objective is a form of let me just the evaluation metric is root mean square or something, which is more like a regression kind of attacks. Looking at the distribution of the available throughputs that is expected, I found out that it's more logical to consider classification for this particular task, because the distribution is not that continuous. That's one fact I have to look at. And the other thing is that the values that are expected to be predicted are more like a kind of quantized values. Because even as part of the statements of the tax, some values of the TP that are less than a particular value was approximated to be 0. This is already intuitive enough to show that other values of the TP that are provided might also be some kind of aggregation or collection just to a particular set. So based on all these things that I found in the problem task, I decided to follow the classification task in coming about the prediction. And after doing this task, after doing this kind of approach, I was able to make a submission that led to a score of 0. specifically, there is none of the TP that was mispredicted, which proved that the approach is logical enough, that while being simple. The second part of the task is to generate a set of APs for maximum TP in terms of any kind of deployments. And the first thing that I have to do in this is to do another set of EDE. And my EDE, which is basically a spatial analysis, to look at in this task, what are we looking for? Basically, they are the sum. And the next question is that, is it possible to get a single set of APs, or there is a possibility of having a lot of a set of AP that end up having the maximum submission? And looking at this, I found out that a single set of AP is not logical, because we can get multiple set of AP, which extend the fact that any kind of solution approach that I'm going to use for this particular task must be something that have a possibility of predicting more than a single set. And for this thing, it makes this problem, which is obviously a combinatorial kind of optimization, trying to get a combination of APs, make it more harder than a regular combinatorial when we are trying to find just a single maxima amongst others. But in this case, we are trying to find more than a single maxima. We want to get basically all the available kind of a combination that leads to the maximum. So for this thing, my approach is just to focus on the permutation of the permutation. Basically, the number of APs that I can select at a point in time. And doing this, I focus on the maximum expected number of AP that was required, which was 4. So I look for the set of all 4 APs in any given deployment, and I try to use my already trained model in executing and getting the prediction. And while the final prediction in the sum and the ones that give the maximum happens to be my chosen set of prediction. And doing this gave me 2 advantages. The first thing is that I was able to predict not only the values of TV for each of the APs, but the sum, and I was able to see clearly that indeed those that gave me the maximum actually gave me the same total TP, which implies that indeed we have more than a single set of APs that can lead to this kind of a maxima prediction. Now, going back to the generated feature and trying to look at what the generated features look like. As I mentioned earlier, I said that what my features is looking at is an interface at large, and also just a very few other kind of feature, which is the AP that I'm actually dealing with, the RSS value of that particular AP, and the interference aggregation, which I mentioned. Basically, looking at the interference in terms of the differences, the normalized ratio, the simple ratio, and finding the aggregation of this led to my feature set that I use in training my LGBM classification model. And also considering the case of the best set of AP, just as an example of what I have here is an example of what I was able to obtain in my simulation. Just this example shows having 4 APs, and you can see that these 4 AP are connected to different S stations while producing the same maximum, the same total throughput, which shows that if we look at this particular table of my prediction, we can see that while the AP that was selected to be the best set of AP happens to be the same thing for this particular case. As you can see, we have AP 1, 3, 4, 5, and 9 being selected. The station that they were connected to are different. Specifically, they are not the same station that were connected to, which I believe are based on the domain of importance of this particular task. There is an advantage into that, like what station that will be used and when they are going to be used, even while we have some AP to be in operation. So, and looking at the total sum of TPs that is being predicted here happens to be same thing. And as I mentioned earlier, this already points into the fact that the maximum set of the best set of APs could be varied, while the total sum are going to be the same thing. Thank you for your time and for your audience, and I will look up for your question. Thank you so much.
Thank you very much for the presentation. And as also in the past presentation, we will take questions and discussion under the Q&A, so after all the presentation. Right now, I would like to go to the next speaker, Hamdi. Please welcome to the stage. Hi, Hamdi, good afternoon.
Hello, good afternoon all.
Arabi, can you stop screen sharing so that Hamdi can take
Yes.
over the, yes, thank you. Okay, yeah. Please go ahead.
Okay, hello everyone. My name is Hamdi Bakos and I am an engineering student at École Polytechnique de Tunisie. I'm going to present my solution for the next Wi-Fi throughput prediction hosted on Zindi. Let's start with the table of content. We will define our problem. We will talk about the data preprocessing, feature engineering, and model implementation. So the goal is to use machine learning to predict the achievable Wi-Fi network throughput for a given subset of access point, transmitting simultaneously using coordinated spatial reuse, CSR, in the multi-access point coordination framework. A synthetic dataset has been provided with data from multiple random wireless LAN deployments. So this is how the data looks like. The orange part represents the received signal strength indicator at each deployment. The blue part represents which access points are activated at transmit opportunity, and the green part represents the value of the throughput of each access point. So for the data preprocessing, the primary task is to transform datasets by removing the RSSI matrix and adding a new feature as columns labeled API STIJ to represent the signal strength between access point and stations. This process will result in 5 unique datasets based on different topologies. Either we have 9 station, 18, so on, up to 36. To create these new features, the API STIJ values is considered only if the corresponding API access point is active and the nearest station's AP is also active. Otherwise, the value is 0. The next step involves transforming all dataset to match the shape of the dataset with 9 station topology. Consequently, all station linked to a specific AP can be treated as a single station, with the main difference being the RSSI between the AP and the station. The 5 topologies are combined into a single train and test dataset. So we ended up with the following features. These features can be categorized in the following groups: access point, AP1 to AP9, deployment, signal strength indicator between access points and stations, namely AP1 STA1 to AP9 STA9, a total of 81 features, and then the throughputs, which are our labels. So for the feature engineering part, we considered the following hypothesis from the perspective of a particular station. First of all, the signal emitted by its associated access point AP can be considered as the desired or useful signal. Signals emanating from other APs that are active at a given transmission opportunity can be regarded as interference signals. The global interfering signals at the station is the sum of all interfering signals from various APs, expressed in terms of power. So we are able to create 9 separate data sets. Each access point has his own data set, which will be treated separately. A new feature can now be created, namely difference, which is the difference between the useful signal and the interference signal, and division, which is the useful signal divided by the interference signal. So this is an example of how, for example, for API1, this is how the data would look like. We have the AP1 station 1 column, the RSSI value. We have the interference value, which we showed that it's the sum of the interference signals in terms of what, then it's converted back again to the decibel scale. And we have our created features, difference, division, and then we have the throughput of the corresponding throughput. So for our machine learning model, there is a very key simplification part here in our model. First, the problem can be transformed from a regression problem to a classification, because we identified 13 unique values of throughput. For the model part, we first used an XGBoost model with the following hyperparameters: number of iteration by default 100, learning rate 0.2, max depth 15, and number of classes as shown earlier 13. So we can see our model performance. We were able to predict the throughput with an accuracy of 100% by all metrics. And for the feature importances, we have the two created features as the most important features, especially the difference, because it's in the decibel scale, which is logic, I think. Because we did so good with an XGBoost model, I thought maybe a simpler model will do the job. Will do the job either. So we opted for a decision tree model with default hyperparameters. Our decision tree models did also an excellent job. We have the mean squared error for all access points that are to be 0. So as a conclusion, our problem is simplified by turning it into a classification problem with 13 unique throughput values. New features were created to represent the difference and division between useful and interference signals. A simpler model was chosen for faster training, resulting in an efficient and effective solution for the given challenge. and the model performs 100% accuracy. So thank you for your attention.
Thank you very much. Right now, we are going to go into the Q&A or the discussion. So I'd like to invite Vishnu to take on the moderation of the Q&A. But before we start, I'd just like to inform everyone on Neural Network. You should refresh your browser so that we have extended the time for the session. So you should refresh your browser to view the rest of the program. So over to you, Vishnu.
Thank you very much. And yeah, thank you, colleagues, for that excellent set of presentations. I will look at a set of questions, and we have Boris, who has taken the time to come here. So I will get to him also if his time allows. So first question, I want to ask Gaurav. So Gaurav, in your slides, it's a very nice formulation of the problem statement. Thank you very much. The assumptions which you are taking for the interference between stations and APs, right?
Mm-hmm.
Yes. Especially in slide, if you look at the slide 4. So in slide, if you compare your slide 3, slide 5 and slide 4. If you compare slide 5 and slide 4, the station AP pairs seems to be slightly different, because you're taking stations under the same AP in slide 5 and different APs in slide 4, I think. Could you explain your choice of the pairs of stations and APs there? Because the reason I am asking is, if you calculate the interference, the stations under the same AP may not interfere. I think like Hamdi explained just now. Hamdi is basically looking at summing up all the throughputs under the same AP. Okay. That's why I'm asking. So if you look at your slide 5, yeah.
Okay, should I share the screen?
Yeah, you can share. Yeah.
Okay, I guess that will lead to the best explanation. So first, the first thing that I want to address is the stations are different. Okay, so this is slide number 4 and this is slide number 5. All I did is add 2 arrows, you see. So basically I want to compute the throughput of this AP-STA pair. So I just added 2 more arrows over here, dotted arrows, showing the interference. So there is, I did not change the access point. So this is first part of clarification that I want to make. And the next part of the question was, how did I choose my AP-STA pair? All right, so here's the thing. When I was doing the problem, my apologies, but I kind of ignored this statement that people have made before. So I'm sorry, I may not be able to go to the exact. So this thing, right, that between 1 and 5 STS are associated with each and every AP, this grid cell arrangement, I ignored that. So I considered a more general topology where the stations are, scattered anywhere and not associated with any AP. So it's more general. So yeah, I guess so. That's why I guess this will lead to a more general solution. But I guess I missed one part of the question, if that can be repeated.
Yeah, if you look at your right side, RSSI 2.2 and RSSI 1.2 and RSSI 3.2. So in all of those, basically the second part is basically the same. So that's why I was asking. Whereas I believe in Hamdi's case, as he explained, he has basically looked at the other pairs, not under the same AP. So that was my question.
Oh, no. Okay, so let me be clear. So RSSI, this 2 is the access point, and this 2, the next 2 is the station. So RSSI 2,2 is between RSSI 2,2 is from this AP to this STA. Okay.
Okay.
Then these are the interference between 1 to 2, RSSI 1 to 2 and RSSI 3 to 2. So these are the interference components. This is the primary one. Okay.
Okay, interesting. Yeah. So this in combination with your global without limitation approach. I think that's where what makes it. Yeah. Okay.
Yeah,
okay.
I consider like arbitrary, because that pairing can also help when developing the heuristics, because if the number of APs are large, we may not want to do this brute force that I did. That's where this clustering can help.
Yeah, I think your approach is quite interesting. While you were presenting, I was looking at the similar applications in cellular, for example, right? And there you have a strict cell-based strategy, and there how to apply this is also a good question. And maybe in your case, the cell edge scenarios your strategy may be better. I'm not too sure.
Right.
But
Cell
I think
edges,
it
yes.
is. Yeah. I think that is quite interesting. Just hang on for a moment. I want to ask Hamdi this question. Hamdi, you basically turned it into a classification problem. I don't know if that is true for everybody else or not, but that's an interesting classification problem. I think the third. By the way, I think your data exploration was very, very, very well laid out. I think it was quite nice. Thank you so much.
Thank you.
The 13 unique values, that's where the problem is. I think you know the domain quite well. From your exploration, it was quite clear that you know the domain too. The problem which I feel is with the scalability of the approach that you are, in this particular case, it may work, but I think in the other, in a larger scenario, for example, like
yes,
Gaurav by mistake. Yeah, exactly. Could you comment upon this? What would you do in case of a larger scenario?
Well, I think in real world data, I would opt for regression problem. I think also the performance would maybe decrease a little bit, but I think it will maintain a good performance. The model can achieve really quite interesting results, but not as this challenge, because it's a classification problem. It's easier, that's it.
Yeah, interesting. Yeah. I think that would be nice. The second problem that it's not clear how you solve the second problem, Hamdi. Did you also look at a combinatorial approach like Gaurav explained, or did you use something else?
I didn't understand you quite well.
The problem two. How did you? What approach did you apply for problem 2?
You mean identifying the best access point? Just a little bit. I just wanna remember what my approach was. Just 1 minute, please.
Yeah, maybe Vishnu, as Hamdi is preparing, we can take Boris. I
yes.
Yeah, Boris has maybe some few words to say.
Yeah, unfortunately, Boris, I believe had to leave. Yeah,
I can answer if you want.
Yeah, sure. Yeah.
Okay.
Indeed.
So my approach, identifying the best group of access points for each deployment, was the following. For each deployment, we will distinguish 4 possible cases. 1 access point transmitting at the transmission point, 2 IPs, 3 and 4. And for each case, the best group of access points is the group where the sum of the throughputs of that group is the highest. So we use the sum of the throughputs as a metric of distinguishing the best group of access points.
Okay, yeah, that sounds good. Sounds good.
Vishnu, I would like to make a comment for both, since we are going for the paper version of this. So here is what I want to talk about: the heuristics. What to do in the larger scenario. The motivation comes from baseball, actually. So there are various metric which will decide the throughput. All right. So one is the primary RSSI, and then there are many secondary RSS, which are the interference parameters. In baseball, this happens. A player can perform in a various way. Can you combine all that to one metric that will classify the player?
Yeah.
I forgot what this is called. I know it because I interviewed for Cleveland Guardians. So so what we can do is, if we can see if it is possible to club all the three metrics, all the metrics features into one feature that will tell what the throughput is. And then the minute we have that, we can arrange all the pairs in descending order of this value, and then apply a greedy approach, and that will do the job. Of course, I have to think more about this, but this is the direction in which I'm thinking.
Yeah, I think that's the interesting thing, interesting approach. In fact, if you look at Hamdi's analysis, he seems to have taken the feature approach that you are saying, but not the complete aspect that you're saying. Interesting, very interesting. Can I ask Arabi? Arabi, do you where did you consider the max limit of 4 that is applied in the second problem statement? There is a as David explained, there is a maximum number of 4 access points that is taken. In your could you show in your code? Where do you consider the maximum number of 4 access points?
Thank you so much. I actually consider this in my coding, because the first thing I look into is that if I decide to go into the total number of cases that we have, which is like, let's assume maximum 9 connected to a single station, then the number of possibility of chances will be higher, which was what led to me thinking of what next is to do, and that was why I tried to decide on focusing on the maximum numbers that was provided, or was stated that we have to use. And by doing so, and looking at my code, I basically focus on the maximum size. I have up here the site counts. The first part here is talking about site count of 1. That is, I'm looking at the maximum possibility of me using a single AP to be connected, and that is what I meant by site count of 1. And that's one led into its own result. Basically, in this particular case, I can only get a single kind of connection. But whenever I go into using 2, then the number of possibilities increases by this thing, because the chances of 2 APs connected operating together and getting a more refined total throughput is higher, because one could be having a very, and the reason for this is that the station that they are connected to might be far apart, and if they are far apart, the interference will be minimal. And when the interference of these stations are minimal in terms of the APs are connected, then they tend to have better throughput, and their sum can be as great as possible. And this is why when we have more than a single AP, then the possibility then changes. And the possibility then changes. And that is why we experience having a lot of choices as I have here. And the same thing, I basically follow the same thing for different site counts. And I stop my site counting at the count of 4. which is what my notebook explained. Like when I have a maximum site count of 4, what do I get? Obviously, this one gave me the maximum possibility of combinations. And to answer a question that was not asked actually, in terms of scalability of my approach and the other thing, and while looking at the problem and while considering the fact that these APs might be more and the number of things could be more, one thing I try to consider is the distance between the stations, because I have a little bit of background in the communication. I understand that distance is also important in terms of considering the interference between stations or APs, to think about these two together. And because of this, I try to implement something that can be used to detect interference based on distance. But I stopped this approach because I see that the problem at that is simpler than going into this kind of complex approach. But when we have something that is more complex, it's more logical to think about some kind of distance metrics that can be related to the throughputs when we have any kind of APs connected to these stations.
Oh, thank you very much. Yeah, I think that distance approach is quite interesting. I think you're right. In this particular data set, it may not be so applicable, but I think in real life it may be quite applicable. Yeah, thank you so much for bringing in that aspect. Can I ask you, in your second problem statement, did you also use a combinatorial approach, or did you did you look at classification method?
Yes, actually, I did both. I started up with using regression, but when I went back to look at the data set and look at the types of tips that I have, I noticed what every other person are noticing at later stage, which is the fact that the possible number of classes are 13 and they are normal constants. And that was why I resolved into classification. While using regression with my approach, I got a very, very low MAPC. And if I could recall, I got something like 0.00 something as my MAPC. And which is why I have to look back at what could be the missing parts. And of course, I don't expect to get a 0 MAPC because this is a regression, cannot just get this kind of thing. So I decided to first look at it in this way. Why not move my prediction to the closest class, just like a kind of quantization? Any prediction that I have, why not move it to the closest value that is available? And when I did that, I noticed that the MAPC value cancelled and becomes 0. And I'm like, and then what led to like, it seems I don't need to waste my time in trying to go for regression where classification will make it simple. Of course, in a kind of more bigger scenario, because I observed that the result that were, the TP that was given to us are actually quantized. If we are given a read throughput that is not quantized, if it's decimal in nature, I believe my approach can be amenable to using normal regression, because I try to focus on getting the features per AP and considering the station that each of these APs are connected to. If I have a single AP2 and the AP2, the first thing is that what is the station that it is connected to? According to the problem statement, we are told that each of the stations has a maximum capacity in terms of AP that could be connected to them. Then if I try to arrange the RSSI value of all the APs available, considering each of the stations, I could see the one that is more prone to be connected to these stations in terms of the one that have, I think the maximum RSS values are the ones that are more to be connected to these stations. And I did this for some of these examples, and I see that it's easy for me to group which is connected to which. And from that approach, if I want to go to the next thing of finding the features, I want to find the features for AP1. Then I look for which of the stations was AP1 connected to. Since I know what station AP1 is connected to, then looking at the RSS value of the interference is more about looking at all other APs in terms of their interference with the station 1 that my particular AP was connected to. I don't need to worry about the connection of those AP to their own base station. I need to worry about their interference with the present base station, which my present AP is connected to. And that was what led to this selection of AP's RSSI values, because we are given a
Very
matrix.
interesting. Yeah, I think that's super interesting. Yeah, thank you very much. I think thank you for answering all the questions, and it's quite diverse set of solutions and very interesting solutions from all three of you. Thanks to David and Boris for taking the time and coming with this problem statement. Thomas, back to you.
Thank you so much, Vishnu, and thanks everyone for the time, making yourself to present, and as well as we are looking forward for the paper that will come out of this work. And I would also like to give thanks to everyone who joined on the neural network, who joined us, asked questions, or just interacted with us. Thank you very much. We have more webinars. The challenge will launch the challenge this year as well, 2023 edition. So we'd like everyone to participate and be with us in the 4th edition of the ITU AI and Machine 5G Challenge. Thank you very much, and I wish you have a lovely day. From me and my colleagues, I would say thank you and have a good day. Bye.
Thanks.
Thank you so much for your time.
Thank you, guys. Bye-bye.
Thank you so much, guys.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.